Hello, everyone. Welcome to Physics 205. So in this lecture, I want to talk about work and energy, um, something called the work energy theorem, and then also conservation of mechanical energy. When certain situations hold, the total mechanical energy of a system can be conserved, right? Can be constant. So let me start off by giving you some definitions. So the first definition is work. Like, what does work mean? How is it defined in physics? So work is basically the mechanical transfer of energy. So it's a transfer of energy due to the pushes and pulls of forces, right? So it's due to the forces either acting on the object, um, somehow either they could be contact forces, they could be long range forces, right, acting on the object. And it's a transfer of energy either from the environment to a system, which would be like positive work, or from a system back to the environment, which would be negative work. So either positive work can be done on a system or negative work can be done on a system. Okay, so how do we calculate work? Well, we're going to keep it simple and we're going to deal with just work done by constant forces. So the force is constant, the force doesn't change. So here's an example here where I have an object and I have a force applied. So the force F here, it's a vector, right? And this object is going to undergo a displacement delta x, and I have it drawn in this direction. And I want to calculate the work done by this force F. Okay, what is the work done by this force F as this object undergoes this displacement delta x? And it turns out it's going to be the force times the displacement, but it's only the parallel component of the force. The component of the force that acts in the same direction as the displacement, that's the only part of the force, the only component of the force that's going to matter. Okay, so you can see the equation here. The work done is equal to the parallel component of that force, parallel meaning in the same direction as the displacement, times the displacement. So it's a force times the displacement, but it's just the parallel component of the force. So if we have our original vector F, how do I find this F parallel here? Well, using right triangle trigonometry, right? It's basically like finding the components that's in the direction of the displacement. If I know my angle, so the angle theta here is the angle between the force vector and the displacement vector, then F parallel is simply going to be F times cosine of theta. So if you look at the formula here, I have it right now as F cosine theta times delta x. So it's basically the work is simply the component of the force in the same direction of the displacement times the displacement. Okay, now the other component, which is like the perpendicular component, right? The component that's perpendicular to the displacement, that component does no work, right? It's not going to contribute to the work done on this object, right? Only the parallel component will contribute to the work. Another thing to note is that work is actually a scalar value. So it has a magnitude, right, in units, but no direction, right? It's not a vector. It doesn't have direction. You calculate it by using two vectors, the force and displacement, but work itself is just a scalar value. Now, the units are, since it's a force times a displacement, it's Newton times meters, but that has a special name, which we call joules. So this capital J here means joules. So work is going to be measured in joules. Okay, so again, this is just a single force acting on an object. What if I want to calculate the work done by several forces acting on an object, called the net work done? So to do that, let me jump on the iPad to explain this. Okay, actually, before I talk about how to compute the network, and there's a couple ways you can do it, let's quickly review how to calculate the work done by each individual force. So let's say I want to calculate, I have this object here and have these 5 forces acting, right? I have F1, F2 acting at this angle with respect to the horizontal, F3, F4, and then I have the weight of the object acting down. Let's assume that the object undergoes a displacement to the right here, so my delta x to the right. And I want to calculate now, I want to calculate the work done by F1, the work done by F2, and so on. So the work done by F1, by that first force there. I'll just call this WF1. So by that, I mean the work done by F1. Well, that's going to equal the magnitude of the force, whatever that is, F1 in newtons. I'll just do this in general right now, times delta x, the displacement, right? The magnitude of the displacement, times the cosine of the angle. But what angle am I looking at? Well, I'm looking at the angle between the force and the displacement, which in this case, if they're pointing in the same direction, that angle between them is 0 degrees, right? So this will be times cosine of 0. But cosine of 0 is equal to 1. So the work done by F1 is simply going to be F1 times the displacement, right? Whatever those values are, and it'll be in the units of joules. Okay, what about the work done by F2? So this will be WF2. Well, that's going to be F2, right? That magnitude times the displacement times cosine of the angle theta, right? And there's, because I don't know the actual values, I'm just doing this in general, you'd have to know the angle, know the magnitude of the force F2, know the magnitude of displacement. You plug those values in, and that will give you the work done by this force F2. So notice here, it's only the parallel component that's going to matter, right? That's where the F2 times cosine of theta comes in. Okay, so that also will be in joules. Now, what about the work done by F3? So WF3. Well, that's going to be F3 times the displacement, wherever that is, times cosine. Now, what is the angle in this case? Well, if you look at this, right, F3 is pointing to the left, the displacement is to the right. What's the angle between those two vectors? It's 180 degrees, right? They're exact opposite direction. So this is cosine of 180. But remember, cosine of 180 is equal to -1. So this is going to be negative F3 times delta x in joules. So basically, in this case, F3 is doing negative work on this object. As this object moves to the right, the force is acting to the left, that work done by F3 is going to be a negative value. Okay, what about work done by F4? So work done by F4. So WF4. Well, that's going to be F4 times delta x times cosine of the angle between them. But what's the angle between? So F4 is straight up, and then displacement, that's 90 degrees. And remember, cosine of 90 is equal to 0. So this is simply going to be 0 joules. So, and we kind of already do this, right? Remember I said earlier, whenever a force is acting perpendicular to the displacement, it's not going to do any work on the object. Okay, and we can see that by plugging it in, because cosine of 90 is equal to 0. So that also tells us that we have no work done by F4 on this object. And this, we're going to see the same thing with the weight too, right? So if we want the work done by the weight, so work done by the weight, W, well, that's going to be the weight times delta x times cosine. But what's the angle between the weight vector and the displacement? That again is 90 degrees. And cosine of 90 is 0. So that force also does no work on the object. So really the only forces that are doing work on this object are F1, F2, and F3. And with F2, it's only the parallel component, right, that does work. In F3, the work done is negative, right? These are both positive works, and in F3 is going to be negative work. Okay, so that's in general how you calculate work done by a constant force. It's always the force times the displacement times cosine of the angle, where the angle is the angle between the force vector and the displacement vector. Okay, how do I calculate the net work done by all the forces acting on an object? So let me do an example of that on this next page here. So let's say I have this object, right? These are the forces acting. So I have F1, F2, F3, F4, and then displacement delta X to the right. And I want to calculate the net work done by all of those forces. So it turns out there's two ways you could do this. The first method is I could find the net force first. How do I find the net force? Well, that's going to be the sum of the forces, right? That'll be F1 plus F2 plus F3 plus F4. You'd have to add those forces, and they're vectors. You have to add them vectorially, right? We could actually do this graphically if you want. Here, I'll do it over here. Let's say this is, I'll make a little coordinate system here. I want to move F1 so that its tail's at the origin. So that would say is F1. Then I'm going to add F2, so I move the tail of F2 to the tip of F1. Let's say it does this. This is F2. Then I add F3, which is going to be back up a little ways, right? Tip to tail. And then finally add F4. So this is F3. It's getting kind of crowded here. And in F4, I'm going to move the tail of F4 to the tip of F3. Let's say it does this. And then if I draw a vector from the tail of the first one, tail of F1, to the tip of the last one, tip of F4, that's going to be my resultant vector, right? That'll be F net. That's F1 plus F2 plus F3 plus F4, right? It's tip to tail. So if I know that net force, and I know the angle that net force makes with the horizontal, or sorry, with the displacement. Remember, the displacement is just off to the right in this case. So in this case, it is just the horizontal. Then I can use my usual definition for work, right? So the net work, I'll say W net, is going to be the net force times the displacement times cosine of the angle, just like before, but now the angle is the angle between the net force and the displacement. Okay, so that's one way you could do it. You could add up all of the forces first and then just use your original definition for the work done. It's the force times the displacement times cosine of the angle between them. By the way, this really only works as long as all of these forces undergo the same displacement. Okay, that's sort of the key thing here. But for everything that we do, you could use this method and you would be fine. Second method, and this second method is actually better, I think. So second method. It's more general, the second method. In this case, what you do is you find the work done by each individual force first. So I'd find the work done by F1. So that would be F1 times delta X times cosine, I'll call it theta 1, where that angle, theta 1, is the angle between F1 and the displacement, right? Then I'd find the work done by F2. So that would be F2 times the displacement times cosine of theta 2. Then I'd find the work done by F3. So that'd be F3 times the displacement times cosine of theta 3. Then the work done by F4. So F4 times the displacement times cosine of the angle theta 4. And then finally, to find the net work done, you simply have to add each individual work. So the net work is going to be the work done by F1 plus the work done by F2 plus the work done by F3 plus the work done by F4. And that will give you the net work. These two methods, so the first method where I found the net force and then calculated the net work using the net force, and then the second method where I find each individual work, right, separately. So I found work due to F1, F2, F3, F4. When I add them together, I'm going to get the same answer as the first method. These will be exactly the same. Okay, as long as each force undergoes the same displacement, you're going to get the same answer. So either way works. Second method is probably just better in general. It's a more general method. Okay, and actually, remember, whenever you have a force that's perpendicular to the displacement, a lot of these will just be zero as well, right? So many of these works could just be zero. Okay, let's go back to the handout. Okay, so as an example, let's say we have a 50 kilogram crate, and it's being pulled with a force of 100 newtons at an angle of 30 degrees with respect to the horizontal for 5 meters over a frictionless surface. And we want to calculate how much work was done by that force F, how much work is done by the normal force, and how much work is done by the weight W. Okay. Actually, I guess it'll be easier if I jump back on the iPad. So let me jump on the iPad to do this problem out. Okay, so the first thing you should do is draw a picture, right? Let's say this is the floor. I have this crate. And then acting on it, I have several forces, right? I have this force F. It's acting at an angle of 30 degrees with respect to the horizontal. What else do I have? Well, I have the weight, right? The gravitational force acting down. That's always equal to mg. And then I have a normal force that the surface exerts on the crate upward. And there's no friction, right? It's a frictionless surface in this case. And we also know that this crate is going to undergo a displacement to the right of 5 meters. So delta x here is going to be 5 meters. And we know that the force, I guess, is 100, right? The magnitude of F, I'll just write as F, is 100 newtons. And that's it, right? Okay. So we want to calculate how much work is done by that force F. So let's start with that. So the work done by the force F. Well, by definition, it's going to be the force times the displacement times cosine of the angle between the force and the displacement, which is 30 degrees. So in this case, it would be 100, right, times 5 times cosine of 30. And if you work that out, that turns out to be 433 joules. Okay, so that is the work done by that force F. Okay, what about the work done by the normal force? Well, in order to find the work done by normal force, we need to first compute the normal force, right? Let's do that first. So how do I compute the normal force? Well, I could use the fact that I could use Newton's second law, right? In the y direction, the sum of the forces in the y is equal to MAY. But this crate is not leaving the ground, right? It's not moving in the y direction, so that's going to be 0. So I want really the y component of the normal force plus the y component of F plus the y component of the weight, and that's got to equal 0. And I'm assuming that my coordinate system is like this, where y is just upward, right? So x is to the right and y is vertically upward. Okay, so in this case, how much of the normal force vector is in the y direction? All of it, right? So I take the entire n. How much of F is in the y direction? Well, just the y component of it, but we know how to find that. That's simply going to be F times sine of 30, right? That would be the y component of F. And then the weight, it's all in the y direction, but it's negative, so it's going to be minus mg. And now it's going to equal 0. So if you solve this for n is going to be, I'll bring mg to the other side and subtract F sine 30. So let's see, this will be 50 times 9.8 minus 100, and then sine of 30 is like a half, right? So this is a half here, 0.5. And if you work this out, this will be, I guess it'll be 490 minus 50, right? Which is 440. So this is 490 minus 50. So 440 newtons. I'm using N for normal force and N for newtons. Just be careful on that. Okay, here This stands for normal force. This is just the units in newtons. Okay, so now I can calculate the work done by N, right? The work done by that normal force is going to be the normal force times the displacement times cosine of the angle between the normal force and the displacement. But what is the angle between the normal force, which is pointing straight up, and displacement to the right? It's 90 degrees. So this is like cosine of 90 here. And remember, cosine of 90 is 0. So it doesn't even matter what these values are, right? It's going to be 440 times 5 times 0, which is going to be 0 joules. Because the normal force is perpendicular to the displacement, it will not do any work on the object. Okay, and we're going to find the same thing is going to be true for the weight, right? If I calculate now the work due to the weight, it's going to be the weight times the displacement times cosine, and the angle between that weight vector and displacement vector is again 90 degrees. So remember, the weight is going to be mg, right, which is 90. Sorry, mg is going to be 490, right? The weight is 490. It's 50 times 9.8, which is 490. So if I want, here, let me write it out one more time. So weight is mg times delta x times cosine 90. So this will be 50 times 9.8 times 5. But doesn't really matter because, again, what is cosine of 90 degrees? Cosine of 90 is 0. So this is going to be 0 joules. Why is that the case? Because this vector, the weight vector, gravitational force, is perpendicular to the displacement, right? It's a 90-degree angle with the displacement. So it's not going to do any work on the object. Okay, so if you recognize that right away, the normal force and weight are perpendicular to the displacement, you could have immediately said, oh yeah, they're going to be 0 joules. So the only thing really doing work on the object was that force F. Okay, another example. So now you're told a 50-kilogram crate is pulled 40 meters along a horizontal floor by a constant force exerted by a person. That the magnitude of that force is 100 newtons, and it acts at an angle of 37 degrees with respect to horizontal. Now you have friction. It says assume the coefficient of kinetic friction between the crate and the floor is 0.1. Now we want to determine the work done by each force acting on the crate and the net work done on the crate. Okay, well, again, let's draw a picture and see what's going on here. So I have, here's my floor. Here's the crate. I have the force that the person exerts. So I'll call it FP. And that's an angle of 37 degrees. And I know the magnitude of FP is what, 100 newtons, right? So FP is equal to 100 newtons. Then I have, what else is acting? I have the weight, right? The gravitational force acting on the object. That's going to be mg. I have a normal force acting up. And in this case, I also have a frictional force. And since it's moving, it's going to be a kinetic frictional force. So it's Fk, right? Acting to the left. Okay, probably I want to use my typical coordinate system, right? Where x is to the right and y is vertically upward. I also know that this crate is undergoing a displacement to the right of 40 meters. So delta x here is going to be 40 meters, right? I hat to the right. Okay, so probably what I want to do here first, let me find the component, since I have my coordinate system, x is to the right and y is vertically upward, let me find the components of F first. Let me find the x component of this applied force, so like FPX, I'll call it, and then the y component, which is like FPY. All right, so how do I do that? Well, I know that the x component, since I have just the reference angle here is just going to be the magnitude of FP times cosine, right, at 37 degrees. We've done this a bunch of times. So FPX is going to be the magnitude of FP, which is 100, times cosine of 37 degrees, right? And it's positive, and in this case, it's 79.9 newtons. And an FPY will be 100 times sine of 37. And that equals 60.2 newtons. Okay, just so we have them, we don't have to worry about this now. What else do I need to know? Well, I'm probably going to need to figure out the normal force. Why do I need to know that? Because remember, the frictional force depends on the normal force. So I'm going to have to find the normal force, so then eventually I can find the frictional force. So to find the normal force, I'm going to use the fact that the sum of the forces in the y direction has to equal MAY, which is 0 in this case. So now I want the y component of the normal force plus the y component of FP plus the y component of W plus the y component of FK. That's got to equal 0. Now, what's the y component of the normal force? Well, it's all acting, right? It's all acting in the y direction, so that's just going to be n. The y component of FP is what we just calculated over here, right? The y component of FP is 60.2. I'll just leave it as y component of FP for now. The y component of W, well, all of the weight is acting in the y direction, but it's negative, so that's like minus mg. And then the y component of the frictional force, there is no y component, right? It's in the negative x direction, so that's 0. So that's going to equal 0. So the normal force here is basically going to be, I'll move the mg to the other side, and then the y component of FP to the other side, so it becomes negative. It's basically going to be the weight minus the y component of FP. So if I work this out, what was the mass of this? So the mass of this crate, it looks like, is 50, right? The M of this crate is 50 kilograms. So this is going to be 50 times 9.8 minus, and then FPY we already figured out was 60.2. So that's going to equal 429.8 newtons, right? So that's the normal force. And then FK, the magnitude of FK now, remember physics is fun, right? We have that formula. It's equal to mu K times N, right? It's proportional to the normal force, the frictional force. So we know mu K was 0.1. That was given in the problem. And then times this normal force is 429.8. So that's going to be 42.98. So around 43. I'll just round it to 43 newtons. Okay, so I have, let's see, I have FK, I have F, I have the normal force. So I think I have everything I need to figure out the work done by each of those forces. Oh, and we know, right, the weight is mg. So that's going to be 50 times 9.8, which is 400 and 490, right? 490 newtons. Okay, so let's find the work done by each force now. So work done oh, it just moved on me. The work done by FP, by that applied force. Well, it's going to be the applied force times the displacement times cosine of the angle between them, which is 37 degrees. So this will be 100 times the displacement was 40 times cosine of 37. And if you work that out, it turns out that's going to be 3,196 joules. Okay, so that's the work done by the applied force. And notice here, it's only the x component that really matters, right? If you do Fp times cosine of 37, that's Fpx, that's the x component, because that's the parallel component. That's the component of that force, right? This x component that's in the same direction as the displacement. That's the only one that matters, the ones that are in the direction of the displacement, right? Or opposite direction. But if it's perpendicular, it's not going to matter, and we'll see that in a minute here. Okay, what about the work done by, I'll do the kinetic frictional force now. So it'll be the kinetic frictional force times the displacement. And then what's the angle between that frictional force and displacement? It's 180 degrees. Right? Remember, cosine of 180 is -1. So this frictional force is going to do negative work on the object. And if you work this out, Fk, well, we just found that, right? What was that, 43? Times displacement is 40 times -1. That's going to be like negative 1720 joules. Okay, so again, this is important here. The friction opposes the motion and it does negative. Notice that negative sign there. It does negative work on the object. Now, what about the work done by the normal force? Well, that's going to be the normal force times the displacement times cosine, but the angle between the normal force and the displacement is 90 degrees. And cosine of 90 is 0, right? So this is going to be the normal force, which is 429.8 times the displacement, but none of that really matters because cosine of 90 is 0, so that's just going to be 0 joules. Because the normal force is perpendicular to the displacement, it doesn't do any work. And then same thing with the weight, right? The work due to the weight here is going to be the weight, which I'll write as mg, times the displacement times cosine of 90 again. So you're going to have 50 times 9.8 times 40, but none of that really matters because now I'm multiplied by 0, cosine 90 is 0, and I'm going to get 0 joules. And then finally, we want to calculate the net work done. Well, since we have all these individual works, we can just add them up, right? So the net work done on the crate is going to be the work done by the applied force plus the work done by the kinetic frictional force plus the work done by the normal force plus the work done by the weight. And if you add all these up, you have 3196 plus -1720 plus 0, and that's going to be 1476 joules. Okay, so this is like the total work done by all the forces acting on the object, right? And really the only two that contributed were the applied force and the frictional force. And the frictional force, the work done by the frictional force was negative, right? The work done by the applied force was positive. Okay, let me go back to the handout and give you some more definitions. Okay, so we talked a lot about work, right? Another definition, because we're going to need to know this when we talk about the work energy theorem, is something called the kinetic energy. So kinetic energy, which is given as K, or sometimes I write this as KE. I think I use KE. You'll see both, so you could use KE here as well. It's the energy due to the motion of an object. So if an object has some speed, some velocity, it's going to have kinetic energy. So how do we compute the kinetic energy of an object? It's simply computed as 1/2 times the mass of the object times the speed squared. Okay, so, and remember, it, because there's no direction, there's a direction to velocity, but it turns out when you square it doesn't have any direction anymore. So these are all just scalar values. Kinetic energy is going to be a scalar value, and it's also going to be in joules. If you look at that combination of units of the kilogram times meter per second times meter per second, that also turns out to be joules. Okay, so you might think, well, since kinetic energy is in joules and work is in joules, there must be some relationship between them, and there is, and we'll talk about that in a second with the work energy theorem. So if you're asked to compute just kinetic energy of an object, it's 1/2 mv squared. Okay, work energy theorem. So the work energy theorem states that the net work done on an object, remember we just learned how to calculate the net work done on some object, is always equal to the change in kinetic energy of the object. So remember, delta here means change in KE. So you can always write a change as a final value minus an initial value. So you can think of the net work done as being the final kinetic energy minus the initial kinetic energy. That's what we mean by the change in kinetic energy. And if I expand this out further, remember kinetic energy is 1/2 mv squared. So I can say the net work done is equal to 1/2 mv final squared, where I have that final speed, right? Final velocity, which really is going to be just a speed, minus 1/2 mv initial squared. So that will give us the net work done on the object. Okay, let's do an example. Actually, I'll jump back over to the iPad to do these examples. Okay, so in this example, you're told a 145-gram baseball is thrown with a speed of 25 meters per second. And we want to calculate its kinetic energy. And we also want to calculate how much work was done to reach the speed, if we're assuming we're starting from rest, the baseball starting from rest. Okay, so what is its kinetic energy? Well, we know in general the formula for kinetic energy, right, K or KE, is equal to 1/2 mv squared. Now, I know the mass, right? It's given as 145 grams. Although I got to be careful. Let's say I want my kinetic energy to be in SI units, so I want it in joules. Then I have to convert the mass in grams to the mass in kilograms. So how do we convert from grams to kilograms? Well, there's 1,000 grams in 1 kilogram, so I can just move that decimal 3 places to the left. Or if you want to use unit conversion factors, let's see, I can multiply by 1 kilogram over 1,000 grams. Right, so this is going to be 0.145 kilograms. The easier way is just move that decimal point. So if you start here, move it 3 places to the left, right? And that'll go from grams to kilograms. Okay, and we know the speed, right? It's 25. So now we know everything we can just plug in. So kinetic energy here is going to be 1/2 times 0.145 times 25 squared. Don't forget to square that speed. And if you work this out, this is going to be like 45.3 joules. So that will be the kinetic energy of the baseball. Okay, and then the second part of the question says, how much work was done to reach this speed, starting from rest? Okay, so remember the net work due to the work energy theorem is always equal to the change in kinetic energy, right? It's a change in kinetic energy, which is going to be KE final minus KE initial. So here, I'll write it out even further. We could write KE final as 1/2 mv final squared minus 1/2 mv initial squared. But if the baseball is starting at rest, that means V initial was 0, which means this whole initial kinetic energy is going to be 0, right? There's no kinetic energy initially because the initial velocity is 0. So that means the net work done is simply going to be that final kinetic energy, which we just found. Right? This is exactly the same thing that we just found. So that's going to be 45.3. joules. Right? So in this case, the net work done on the baseball, because it started at rest, is simply equal to 45.3 joules. It's going to be that final kinetic energy. Right? And again, why does that work? Because in general, the net work is equal to the change in kinetic energy, which is final kinetic energy minus initial, but the initial was 0. So in this particular case, the net work done is equal to that final kinetic energy, which we calculated earlier. Okay, another example. You're told an 85-gram arrow is fired from a bow whose string exerts an average force of 105 newtons on the arrow over a distance of 80 centimeters. What is the speed of the arrow as it leaves the bow? Okay, so again, because we know the force, we know the displacement, we can calculate the net work done on that arrow, right? So in this case, I probably want to convert these things too, right? Make sure everything is SI units. So if the mass is 85 grams, that's going to be the same as 0.085 kilograms. I move the decimal 3 places to the left. And then the displacement here, I'll call it delta x, is 80 centimeters. But if I want that in meters, now I got to be careful. There's 100 centimeters, right? Not 1,000, 100 centimeters in 1 meter. So now I just move the decimal 2 places to the left, be 0.80 meters. So in general, I'm going to want the net work done, if I use the work energy theorem, must equal the change in kinetic energy, which is KE final minus KE initial. Okay, so how do I calculate the net work? Well, the net work is going to be the force times the displacement times the angle between them, right? But if you think about what's going on here, let's see if I can draw a picture of like here's the bow. Oops, that's not very good. Here is the string, probably gonna be stretched out a little bit like that. And then you have an arrow here. And so the force is applied right at this point to the arrow, and it's going to be undergoing a displacement in the same direction. So like the force is in direction to the right and the displacement is in the direction to the right. So this angle here, I guess, is going to be 0 degrees, right? And cosine of 0 is just 1. So in this case, it'll be 105 times 0.8 times 1, which is going to be 84 joules. Okay, what else do we know? Well, we also know that the arrow starts at rest, right? So the initial kinetic energy is going to just be 0. This term is going to be gone, right? Because why is that? Because the initial velocity is 0. So if I plug in 1/2 mv squared and that v is 0, that means the initial kinetic energy is going to be 0. The final kinetic energy, so KE final, that's going to be 1/2 mv final squared. Now, we don't know what v final is. In fact, that's what we're looking for, right? We do know the mass, though. The mass was what? The mass was 0.085 kilograms. Okay, so right now I have this, right? I know that the net work done is going to equal that final kinetic energy, right? Because the initial kinetic energy is 0. So the net work done we calculated was 84. And that final kinetic energy is going to be 1/2 times 0.085. Again, is that right? Yep. And then times v final squared. So now I can solve this for v final. So if you basically multiply both sides by 2, I'll do it that way, and then divide by 0.085, right? That'll give me v final squared. And then finally, if I take the square root of both sides, so v final is going to be the square root, and I know it's going to be positive, so I want the positive root. So if you work that out, that's going to give you around 44.5 meters per second. So that's the final velocity of the arrow. That's the velocity that the arrow leaves the bow at, right? As 44.5 meters a second. So we used the work energy theorem to basically solve this problem, to figure out how fast the arrow left the bow at. Okay, another example. You're told a baseball has a certain mass. Actually, let's immediately convert it. So 145 grams, that's going to be the same as 0.145 kilograms. Traveling 32 meters a second, moves a fielder's glove. Okay, so a fielder catches the baseball and it moves the glove backward by 25 centimeters, which means the displacement is going to be, so called delta x here, is going to be 25 centimeters, which if I put in SI units is 0.25 meters. What was the average force exerted by the ball on the glove? Okay, so here's like the picture. Let's say this is the ball, right? It's moving with an initial speed of 32 meters per second right before it's caught. And then it's caught by a fielder here. So you have their hand. And the hand is going to be exerting a force on the ball that slows it down, right? And it's undergoing this displacement. So the hand is moving backwards by 0.25 meters. So delta x here is 0.25 meters. So basically the hand is doing like negative work on the ball, right? To slow it down so it comes to a rest. Okay, so, well, let's solve this by using the work energy theorem. And what are we trying to find? We're trying to find the average force, right? Exerted. Ultimately, we want the force that the ball exerts on the glove, but we can figure out the force that the glove exerts on the ball first. And then it's just going to be the opposite of that. Okay, so I'm going to use work energy theorem, right? So the net work done is equal to the change in kinetic energy, which is going to be the final kinetic energy minus the initial kinetic energy. Okay, so the net work done is going to be that force, which we don't know what that is, F, times displacement times cosine of the angle between the force and displacement, which is going to be 180 degrees in this case. Right? The force is acting in this case to the left in my example, and displacement is to the right. So that angle between them is 180 degrees. And remember, cosine of 180 is equal to -1. So that's why I'm saying that the glove, the hand, is going to do negative work on the ball to slow it down. So if I plug in here right now, I'm just going to have F. I know the displacement is 0.25, and then now this is going to be negative, right? -1. Okay, so that's the net work done. What about the right-hand side, the change in kinetic energy? Well, in this case now, because the ball is coming to a rest, the final kinetic energy is going to be 0, right? Because that final velocity, V final, is going to be 0. And then the initial kinetic energy is 1/2 mv initial squared. Well, that's going to be 1/2 times the mass of the ball, which is 0.145, times the speed of the ball, 32 squared. So that's going to be like 74.2 joules. Okay, so now if I plug in, I have the net work is equal to the final kinetic energy, which is 0, minus the initial kinetic energy. So this is going to be -F times 0.25 is equal to -74.2. And then if I divide both sides by -0.25, then it turns out F here is going to be 296.8. That's newtons. Okay, so, and again, that was actually the force that the glove exerts on the ball. But by Newton's third law, we know that the magnitude that the ball exerts on the glove is exactly the same, right? It's going to be in opposite direction. So if we want the force that the ball exerts on the glove, it's going to be to the right. But the magnitude is exactly the same. So they're asking for what was the average force exerted by the ball on the glove. We found the average force exerted by the glove on the ball, but it's the same magnitude, right? So that answer is going to be the same. Right, so the force exerted by the ball on the glove is also 296.8 newtons. Okay, so now I want to give you another definition. We talked about work, we talked about kinetic energy, and then we talked about the work energy theorem. There's another type of energy that comes up, especially in a mechanics class, and this is called gravitational potential energy. And you can think of it, it's a little more complicated than this because it really depends on the interaction between two objects, in this case, the Earth and some object that's near the surface of the Earth. But you can think of it as the energy that an object has due to its vertical position relative to some reference point near the Earth's surface. Okay, so to calculate this gravitational potential energy, I'm denoting it by PE for potential energy, and the G just means gravitational potential energy. There's other types of potential energy, like something called spring potential energy. You could have potential energy due to charges. So there's different ways, or there's different types of potential energy. We're going to focus just on gravitational potential energy. So to compute it, it's simply equal to the mass of the object times g, the acceleration to gravity, right, 9.8, times y here, where y is the vertical position relative to some reference point. Can be whatever you want it to be. It could be the ground, it could be your lab bench, it could be the ceiling. It doesn't matter what you choose as your reference point, because ultimately we're only going to be interested in the change in potential energy. So the change in gravitational potential energy, which is the same regardless of the reference point. So like the initial and final values of the potential energy are going to be different based on what you choose as a reference point, but the change in potential energy will be exactly the same. Okay, so actually let me start by showing you an example of this, and I'll jump back on the iPad to do this, of why it doesn't matter what you choose as your reference point if you're only interested in the change in gravitational potential energy. Okay, so in this example, I have an object and it starts at some location and it moves up to a new location, and I want to calculate the change in potential energy. In the first case, in this left-hand case, I'm assuming that the top of my lab bench is my reference point. So that's where I have like y equals 0. So then the first location would be y1, which we're going to say is 1 meter, and the second location is y2, which is 3 meters. So it's moving from 1 meter up to 3 meters. And I'm going to calculate the change of potential energy. Over on the right-hand side, it's exactly the same situation. This object, think of it as a ball or something, is undergoing the same displacement upward. I want to calculate the change in potential energy. But now I'm using the ceiling as my reference point. So the ceiling has a y value of 0. And now y1 is below the ceiling, right? So it's going to be negative. In this case, it's negative 2.5 meters, let's say. And then y2, let's say this ball is like 0.5 meters away from the ceiling. So if the ceiling is 0, this will be negative 0.5 meters. Okay, so let me calculate the change in potential energy using both of them, and you'll see that you're going to get exactly the same value. So it doesn't matter if we use the lab bench as our reference point, as our 0, or the ceiling as our reference point, as the y equals 0. So again, in both cases, I want to calculate the change. So I want to find the change in gravitational potential energy. So that's going to be like PE final, I'll call it PE 2 in this case, minus PE G1. And then same thing here. So I have change and gravitational potential energy is PEG2 minus PEG1, right? It's the final position minus the initial position. It's moving from 1 to 2. Okay, so if you write this out, remember potential energy is the mass times acceleration to gravity times that position y2 minus, in this case, mass times gravity times y1. And it's going to be the same thing over here. So mgy2 minus mgy1. If you want, you could do a little bit of algebra here. You could factor out an mg. So then you just have mg times y2 minus y1. Same thing over here. y2 minus y1. And now if I plug in, so this mass was, did I give you a mass here? Let's say the mass is, 2 kilograms. I have it right here. So mass is 2 kilograms. So this is going to be 2 times 9.8. And in this first case, y2 was at 3 meters, right, above the bench, and y1, it was 1 meter above the bench. So this is going to be 2 times 9.8 times 2. And if you work that out, that is exactly 39.2 joules. Now, in the right-hand case, where I'm using the ceiling as my reference point, the mass is 2. That's the same. G is the same. But now my y2 was the second position, right, which was I think it was 0.5 below the ceiling. So this is like negative 0.5. And then the y1 was negative 2.5. Okay, so if you're careful here, right, this is going to be negative 0.5, and then I have minus a negative 2.5, which is plus 2.5, but that's just plus 2 again. And of course, we get exactly the same value, 39.2 joules. So it doesn't matter what you choose as your reference point, because ultimately we're only interested in the change in potential energy, and that's going to be exactly the same regardless, right? Regardless of what we choose as our reference point. Okay. Let me go back to the handout for a second here. Okay, so now I want to go off on a slight tangent and describe the difference between what a conservative force is and a non-conservative force is. And the reason why I'm doing this is it turns out the work done by conservative forces is going to be related to the change in potential energy, the change in our case, the change in gravitational potential energy. So a conservative force is one for which work done by or against it depends only on the starting and ending points of motion and not on the path taken. So it only depends on the initial and starting positions, right, of the particular object. It doesn't depend on the path that's taken. So some examples of conservative forces are the gravitational force, which is the one that we're mostly going to be interested in this course. If you have a spring force, that doesn't depend on the initial and ending positions. So the spring force. And then if you were to study electricity and magnetism, the electrostatic force is also a conservative force. Really, we're mostly going to be interested in the gravitational force in this class. Now, what are some examples of non-conservative forces that do depend on the path that's taken? Well, certainly the frictional force would, right? If you were to take a box and drag it from one point to another point, you could drag it straight to the other point. You could drag it like in a curvy motion, and that's going to require a lot more work, right? It's going to do a lot more negative work. Same thing with the tension in a string, like when you're pulling an object, right? It depends on the path that you're pulling. That's going to give you a value for the work. So it'll depend on the path that's taken. Or any applied force while you're pushing an object will also depend on the path that's taken. So in most cases, most forces are non-conservative, right? But the one example that we're going to have, at least in this class, of a conservative force is the gravitational force. Okay, so let me show you how that is going to be related to the potential energy. So what we're going to do, and I'll jump on the iPad to show you this in a second, is we're going to calculate the work done by the gravitational force in lifting an object
from 1.5 meters above the ground to 4.5 meters above the ground. And then we're also going to calculate the change in potential energy of the object. And it says, what do you notice? What we're going to notice is that the work done by the conservative force is going to equal negative the change in potential energy. Okay, so we're going to notice that the work done by the conservative force is equal to negative the change in potential energy. So let me show you that.